In this lecture, we are going to continue our discussion on HMM parameters and how we can use an HMM. Specifically, we'll be focused on the three main tasks that an HMM can do, and we'll briefly go over the intuition for how each of these works. In addition, we'll discuss why these tasks are important, so you understand their purpose in real-world application. Note that this lecture is intended only to be a brief explanation of these tasks, not a complete derivation or in-depth discussion. This is just like the other models we discussed in this course, like the GMM and Q-learning. I have individual courses for each of these models, which do go in depth, and I don't intend to repeat that material here. Furthermore, it would be impractical for you to have to learn a whole course's worth of material. For these reasons, the methods we are about to discuss will not be investigated in depth, but you should get a high-level intuition for how they work. As always, if you're interested in learning more, please ask me for references on the Q&A or through my website. Finally, note that the math parts of this lecture are optional. The goal isn't for you to have a strong grasp of the math, but just a high-level understanding of what we want to do. The goal is to get to the end of this lecture, where I show you the code for how we will use an HMM. Since the code is very short, I wanted to give you some idea of what that code is actually doing. So again, focus on the high-level principles over a deep understanding of the math. Okay, so task number 1, finding p of x. In this case, x is the entire vector of observations, x1 all the way up to xt. And remember that in our case, these represent stock returns. It sounds pretty simple, but in fact, this can get quite complex. Okay, so how do we even begin with solving this task? Well, remember that we are equipped with a graphical model. Let's suppose all I had was a single time-step sequence, that is z1 and x1. I know that x1 depends on z1. I also know that I have two probabilities. We have z1, which has its own distribution, p of z1. It's all by itself, since there are no arrows going into it. We also have p of x1 given z1. We know that this should be a conditional distribution, since x1 depends on z1. Okay, so what can we do with this? Well, in graphical models, we are typically interested in the joint distribution. Luckily, we can use the information we have to find it. P of x1 and z1 is equal to p of x1 given z1 times p of z1. This is just the rule of conditional probability. But we know we only care about p of x, which in this case is just p of x1. Luckily, we know how to do this too. This is just marginalization. In order to find p of x1, we need to sum the joint distribution over all possible values of z1. As you recall, that's just the sum from 1 up to m, if we have m hidden states. Okay, so that was just a very simple case. What if we have a sequence of length 2? Now there are two extra variables, z2 and x2. However, we know how all these things are related, and we now have some idea of what we want to find, the joint distribution. So how do we find the joint distribution over these four variables, x1 and x2, z1 and z2? Well, since z1 still has no arrows going into it, we can start with p of z1 all by itself. Then, we know that x1 depends only on z1, so we can include p of x1 given z1 as before. But we still have z2 and x2. We know that z2 also depends on a z1, so we have to multiply by z2 given z1. Finally, we have x2, which depends on z2, so we have to multiply by p of x2 given z2. As before, we want to find p of x, which is now the joint distribution over the sequence x1, x2. This means that we have to marginalize the full joint distribution by summing over z1 and z2. So notice how we now have two sums over I and j from 1 up to m. Okay, so pretty easy so far. So if we keep following this pattern, what do we get? Well, let's now assume that we have a sequence of length big T. In this case, we can express the joint distribution over the sequences x and z by following the pattern we had before. Notice that the x without any subscripts is the sequence x1 up to xt, and z without any subscripts is the sequence z1 up to zt. As before, when we want to find p of x by itself, we have to sum over all the possible values of z for all the z's. Okay, so that's how we find the probability of a sequence given a hidden Markov model. There's one problem with the previous formulation. Let's consider how long it would take to compute. First, let's look at the product, which is inside all the summations. That's approximately t multiplications, so we say it's O of t. But now, let's consider the summations. We are doing t joint summations, since we have to sum using z1 all the way up to zt. However, each of those individual summations need to sum over m different possible values. So overall, the total number of things I need to sum is m times m times m and so on, t times. In other words, that's m to the power t. So overall, the complexity of this calculation is O of t times m to the power t. You may recognize that this is exponential growth. Luckily, we do have algorithms to overcome this problem, which we won't discuss at this moment. The important thing is to understand that we can do this calculation, and why we want to do this calculation. The reason why we care to find p of x is because, as you know, we need to find the parameters of our model. The parameters of our model consist of A and the mu's and sigmas for our Gaussians. So why does p of x help us find the model parameters? Well, this is nothing but maximum likelihood estimation. This is the same thing we do when we want to find mu and sigma for a Gaussian distribution. Let's suppose we collect a bunch of heights from the people in our class, and we would like to fit a Gaussian model. The mu and sigma that we find should be the mu and sigma that maximize p of x, the joint distribution of the data we collected. For example, we would not want to set mu to be 1,000 feet, since that would make p of x very small. Clearly, the average height of the people in our class is not 1,000 feet. Similarly, for an HMM, we need p of x because that's what we want to maximize in order to find A, the mu's, and the sigmas. So how do we maximize p of x in order to find A, the mu's, and the sigmas? Well, there's actually more than one answer to this question, but here are two. Method number one is to use the classic general method of gradient ascent. Let's suppose that all our parameters are stored in some big vector called theta. Then we find the gradient of the log of p of x with respect to theta, and then we take small steps in that direction. After doing this several times, we arrive at the maximum. Note that, just like maximizing the likelihood of a Gaussian, it's much easier to work with the log of p of x compared to the original p of x. If you would like some references on why gradient ascent works, please ask me about it on the Q&A. Method number two is to use a more advanced method called expectation maximization. This is an algorithm designed specifically for probabilistic models with hidden variables that you need to sum over. Another example is the GMM, which we saw earlier. The details of expectation maximization are outside the scope of this course, but if you want to learn more, you're encouraged to ask about it on the Q&A. Oh, and by the way, this is task number 2 for an HMM. So task number 1 is to find p of x. Task number 2 is to maximize p of x so that we can find the parameters of the HMM, and that's A, the mu's, and the sigmas. But note that task number 1 can still be useful on its own. For example, if we have a sequence and we want to know whether or not it's probable under our model, we can check the value of p of x. If we have several models for different classes, we can check which model gives us the largest p of x to determine which class that sequence came from. For example, we might want to classify stocks as healthy or poor, or good investments and bad investments. So that would be how we can use HMMs to build sequence classifiers. Task number 3 is called decoding, also known as inference. As you recall, our graphical model shows z pointing to x. But in the physical world, what we actually have is x, the observations, and we do not know z. So decoding takes us in the opposite direction. It says, here is x, now give me back z. The intuition is that we want to choose a sequence for z, z1 up to zt, such that the probability of our observations is maximized. So we see that task number 1 appears again, since we are again required to find the probability of a sequence of observations. So let's think about how we might perform this task from a naive standpoint. So we have our observations, x1 up to xt. We want to find the best settings of z1 up to zt, such that the probability of observing x1 up to xt is maximized. As an example of some possible solutions, consider the sequences low, 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 and so on, or high, 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 and so on. That is, sequences of all lows or sequences of all highs. Clearly, these two sequences of z's are probably not the answer. The answer is most likely a combination of lows and highs. For example, consider the following sequence of stock returns. I've highlighted the periods of high variance and the periods of low variance. Clearly, I would like my HMM to return high during the periods of high variance and low during the periods of low variance. So that should give me a larger probability. To be more precise, the exact probability we want to maximize is P of z given x. That is to say, the probability of hidden states given some observations. This makes sense since the observations are actually what we are given. However, notice that P of z given x is just P of x and z divided by P of x. This is just the rule of conditional probability once again. Of course, we know how to find both of these from task number 1. Furthermore, since we are taking the max over all possible values of z, this actually doesn't depend on P of x at all. Therefore, this is the same as maximizing over the joint distribution P of x and z. Now that we know this, the rest is easy. Okay, so let's say we want to find the best possible sequence, z1 up to zt, that maximizes P of x and z. In order to do this, let's simply generate all possible sequences for z. Then we can loop through each of these sequences, calculate P of x and z, and then keep the one that gives us the maximum value. Okay, so that should seem pretty straightforward. Please walk through this pseudocode to make sure that it makes sense to you. Again, I want to reiterate that this is for intuition only. As you recall, there are still m to the power t possible sequences, so in fact, this has exponential complexity. We do have a more efficient way of decoding, which is called Viterbi decoding. This is named after the person who invented the algorithm, Andrew Viterbi. He is also the co-founder of Qualcomm, which you may have heard makes chips that power many of today's smartphones. So I hope that this lecture provided you with some insight into what an HMM does under the hood when we use it. In practice, using an HMM is actually very simple because there are libraries out there which have already implemented the algorithms we discussed. Note that, unlike many other machine learning models, the HMM is not part of scikit-learn. One library I really like is called HMMlearn, which is available for Python. This is not automatically installed with Google Colab, so we'll need to install it using pip. So here's the pseudocode for using an HMM. As you'll see, even though it's not part of scikit-learn, the way that it works pretty much follows the usual patterns. First, we start by instantiating an HMM object. We'll use Gaussian HMM because our model has Gaussian observations. Note that the usual HMM students learn about is one with discrete observations. Gaussians are more useful for us because they handle continuous data. Next, we call model.fit to train our model parameters. As you recall, this sets A and the mu's and the sigmas of each Gaussian. Finally, when we want to make an inference, we call model.predict, and this gives us back Z, the most likely sequence of hidden states. Internally, this runs Viterbi.